Hey everybody, it's my favorite day in the physics calendar. It's Standing Waves and Musical Instruments Day. If you don't have these notes printed, I recommend you have them up in front of you electronically as you watch this, or you have them available to you in print. If you need to press pause and go get them. And let's get started. At the end of this, we should know a lot more about how sound, especially musical sounds, are produced and how instruments are designed and played, including one very special instrument, our voice. So let's get started. I'm going to shrink myself down here so that you can see a little bit more of the screen. First off, musical instruments take advantage of something we call a standing wave. Now, a standing wave is really just an interference pattern with a wave that typically reflects on itself. So standing waves in strings look like these pictures here, and they can be on strings, they can be on all sorts of musical instruments. We're going to deal with strings first because they're the simplest to understand. So where these ends are labeled, those are the nodes. Nodes are places where waves cancel out. So you'll remember that we talked about wave interference last time. And so wave interference happens if we make a pulse and we make another pulse. If we make them at the same time so that they overlap, crest over crest and trough over trough, every time we do that, the waves are going to add up and make a bigger amplitude and a bigger amplitude and a bigger amplitude. That's constructive interference. So that's what's happening at these antinodes in a standing wave. At the nodes, there's destructive interference. Destructive interference, remember, is happening when a wave pulse is made and then it interferes with another wave pulse and cancels out when they overlap, like that. Now, as it turns out, certain frequencies of waves will cause a pattern that seems to sit still. Now, the waves never can, but we call them standing waves because they look like they're standing still. So let's try that out. You can see these incident sine waves, when they reflect back on each other, end up overlapped so that we're always getting a node here and here and here, and antinodes where crests and troughs are oscillating back and forth. So that's a standing wave, and those standing waves only happen at very particular frequencies. If we try this at a different frequency, and I'll restart it, you'll see that we get some sort of interference, but we don't get nearly the same pattern you see it at some frequencies as you do at others. So I've got to have a little damping on to make that work. All right, so you see this is getting some constructive interference, then it kind of dies out, then you get a little constructive interference. That's a frequency that's not one of what we would call the natural harmonic frequencies of this particular string. Only the harmonic frequencies will be sustained. Those harmonic frequencies, they correspond, if you pluck a string, if you drag a bow over, to the frequencies that you actually hear it ring out with and be able to sustain. So objects oscillate easily at these frequencies that correspond to these standing waves, and we're able to tune strings and tubes of air, which is what brass and woodwinds are, so that they play particular frequencies that we want. All right, so let's talk about incident and reflected waves a little bit more so that we understand how a standing wave actually forms. So this is a great little physics clip from some folks down in Australia. Let's push play and watch. So this red line is an incident wave. It'll be moving to the right. This gray line represents what would happen if you had another wave coming the other way, but what actually happens is that wave is just its own reflection. So when we push play, we can watch these waves overlap. And if we pause it at a particular moment, the black wave represents the actual position of this device that the waves are on. The red and blue waves represent the first wave and then the reflected wave. Those two waves overlap, and so you can see where their crests overlap, we get a taller crest. Where their troughs overlap, we get a lower trough. So if we go step by step here, you'll see that there are times where the two waves are out of sync, and so they cancel out, and then when the two waves are in sync, you get these really tall waves. So as it turns out, the same spot over and over and over again never adds up to anything, because for one of the waves, where whenever it's a crest on one spot, it's a trough on the other. So it'll be like right here. And then the other wave, it flips over. Here's that spot again. The first wave is a trough, and the first wave was a crest. So those spots are where these nodes would form. All right. So here is a string that you can see, and here are the numbered frequencies. So we call these natural harmonic frequencies, the ones that can be sustained, the ones that would be made if you plucked a string. We call them the harmonic frequencies. And this first one, the lowest one, is called the fundamental. And the fundamental corresponds to the longest possible wavelength. So when we run this, you can see that just the middle of this string is vibrating. Now, this is actually 5 different movies of the same string. And right as I push play, you'll be able to see the person's hand move out of the frame. When that happens, what you're looking at there is the wave that can result. He just toggled the string just a little bit very quickly at a frequency that was twice the fundamental, and 3 times the fundamental, and 4 times the fundamental, and 5 times the fundamental. Let's watch that again. As you do that, you see that this wave has a node in the middle. This wave has 2 nodes in the middle. This wave has 3 nodes in the middle, 1, 2, 3, right there. So we've made diagrams off to the left of this. Again, this is the fundamental and what we call the second harmonic, which is twice the fundamental frequency, and the third harmonic, 3 times the fundamental frequency, and so on. And what you see is the wavelengths that correspond to these frequencies are getting slower, are getting shorter and shorter and shorter and shorter. These particular wavelengths are the only ones that can form standing waves, because a standing wave has to have the right part of the wave at the end. For a string, the string has to be held on one end and the other, so nodes must form at the ends. The end of the string can't be flopping around. That wouldn't make much of a musical instrument. All right, so I actually have one of these in the room here. So we're going to go full screen here. I'm going to pause it and readjust, and then we'll get started again. All right, what you're looking at here is an oscillator. So this is what we call forced resonance. If I just plucked the string, any of its harmonics could play, but I'm oscillating it at one of its harmonic frequencies. And so you can see this is a node. This doesn't really move much. We've got a lot of movement right here, so it's an antinode. We've got a node right there. This is still, so let's zoom out a little bit and make sure you can see that. So there's my node right there. And then as I scroll over towards the other end of the string, you can see a node at that end. So we've got node, antinode, node, antinode, node. Now that's one full wave, so the length of the string equals the length of the wave. This is the second harmonic. So this is 2 times the fundamental. Now, if I go to a frequency that's half this frequency, that's what I'm trying to drive it at now. Sorry for the shaking there. All right, if I go to a frequency that's half this frequency, then I'll be pulsing in energy at a frequency that's precisely equal to this string's natural fundamental frequency. And you can see that as I do that, we get one big antinode right in the middle. So we'll pivot the camera again, and you can see that we get a node on one end, lots of movement in the middle. That's an antinode, and the node on the other. So that wave is twice as long as the actual string, because we're only getting half of the wave on the string. Now, if I triple that frequency, notice I'm not really turning up the amplitude here. I'm not putting in more energy. I'm just putting it at the right time. And if I triple that frequency, we get one of the other standing waves. This is the third harmonic. So again, let's take a look at what this looks like here. So we've got a node there, and then an antinode, a node, an antinode where the string's really moving a lot. It seems to be kind of flashing around. That's because the frequency of the recording kind of matches the frequency of the string. Here's a node, there's another antinode, and then finally a node. So we've got one full wave plus another half. So this is 1.5 waves. So there's always a mathematical relationship between the length of the string and the wavelength that fits on that string. All right, let's go back to the notes and take a look at something. We're going to flip to the next slide of the notes. And when we flip to that next slide of the notes, what we see here is really just a summary of what we were just talking about. So only certain frequencies of standing waves are possible on a string, and those frequencies correspond with particular wavelengths. Those particular wavelengths are either twice the length of the string, equal to the length of the string, equal to 2/3 of the length of the string, 2/4 of the length of the string, or so on. The fundamental frequency, that's the lowest note that could be played on a particular string, is always corresponds to that longest wave. And all the other harmonics, F2, F3, F4, are just whole number multiples of that lowest possible frequency. So these equations can be used to relate the wavelength that's on the string to the actual length of the string itself, where L is how long the string is, and lambda, remember, is how long the wave is. So in this picture, one wave is from here to there, and then there's a second wave from here to here, and that's why the wavelength is 2/4 of L. It's only half as much. That equation in general form could be used to predict the wavelength of any harmonic on any string. Now, what that means is that there's a pattern to the notes that will come from a plucked string. So let's go to the web again, and let's take a look at normal modes of vibration. And I'm going to zero out these positions here. If we think of a string as really just a bunch of masses that are all tied together with a bunch of strings, the string is really just like a stretched mass, and so it acts a lot like springs. If we pluck it, so press start, so it'll start moving as soon as I do. If we pluck it, when it vibrates back and forth, it looks really chaotic. But what's really happening is that motion is really just a very complex interference pattern of the first harmonic, and the second harmonic, and the third harmonic, and the fourth harmonic, and the fifth harmonic, all happening at the same time. Since the harmonic frequencies are the frequencies that naturally interfere with each other in a way that's sustainable, always having destructive interference at certain points, always having constructive interference at certain points along the wave, it means that when you pluck a string, you actually get a mix of all of these wavelengths and more. So the way I plucked this, you can see that it resulted in a lot of the first harmonic, and that's why when we play it, we see the string going up and down with one antinode in the middle. And you can see that it also gave us a lot of the third harmonic, and that's why you see a lot of motion here, here, and here. The third harmonic has 3 different places where there is constructive interference, and you get oscillating crests and troughs. These pictures down here, these normal modes of vibration, show how much of each one of the harmonics it would take to make all of this motion that you see in the one string. So, that's why when you play a string, you don't hear a tuning fork. When you play a tuning fork, you just hear the one note. But a string doesn't sound like one note because it doesn't play one note. It plays its fundamental, and it plays a bunch of harmonics above that fundamental, which are always whole number multiples. Now, we can actually graph which of these normal modes of vibration is loudest. And one way to do that is in this Chrome Music Lab that I'm going to have you go play around with. It's fun. You're going to take this spectrogram, and when you have a spectrogram, let's just play one note at a time first so that you get a sense of what that looks like and how to use this. When you push your mouse down, depending on where you are, low notes and high notes, you can see that it graphs the lower notes down lower on the screen. Now, if we sing, you can see that there's the fundamental, and there's these other lines. By the way, when you speak, of course, you're varying the frequencies quite a bit. So let's play a flute. And so the higher pitches means a higher fundamental. But you see, for each one of these notes, there are frequencies above that fundamental, because stringed instruments and brass instruments like a flute play more than just their fundamental, and that's what gives them that musicality. All right, so as it turns out, there's another more quantifiable way to measure the sounds that a particular instrument makes. It's with an FFT graph. So let's take a look at that. So I'm going to sing again. I apologize. And we're going to record what that looks like. So hang on just a second here. La. Now, let's explain what this graph looks like, and then we'll correspond it to what's over here. So this is actually the motion of the microphone, and the motion of the microphone is, of course, dependent on the sound waves that hit it. Well, those sound waves that hit it are driven by the motion of my vocal cords. So in some ways, you could think about this green line as a map of what my vocal cords were doing as I was singing. Now, this bottom graph, we have to look really carefully at the y-axis and x-axis to understand what's here. So amplitude, that's loudness. So the taller one of these spikes is, the louder that particular noise is. Frequency, that's the particular pitch of that noise. Well, what you see is a pattern. Let's hit examine here. The lowest note I was producing was about 230 hertz or so. Now, if I put my cursor over the next spike, you see that that's about double. We're somewhere around 460 hertz or so. If we go to the next spike over, we're somewhere around 3 times the fundamental, and then 4 times the fundamental, and 5 times the fundamental, and so on, which means these spikes, they correspond to the frequencies that are made by these standing waves. Your vocal cords act just like strings. You tune them to a particular fundamental, and then they also play overtones in whole number multiples above them, and you can see there are some overtones that are much higher frequency. If we look in the notes on the next page, you can see that what I've got there is an FFT graph of a cello's E note. And this chart is here to help you understand that the first spike that you see corresponds to the cello string vibrating with one antinote in the middle. That's the fundamental frequency. And on this graph, you can see this is about 500 hertz, 250B is somewhere in the middle, so this is somewhere around 200 hertz. Then the second harmonic can also be played at the same time. The string can have all of these harmonics going on at once. They simply pass right through each other and interfere with each other, and that's why we saw in this normal modes of vibration, we saw the complicated way a string might actually look if we could look at it close up and at high speed. It's because all of these different harmonic frequencies are happening simultaneously. Now, if we go back to the notes here, the taller the spike, the louder that particular resonant frequency is. And it's not uncommon when you play a stringed instrument with a bow to actually get the second harmonic louder than the fundamental. So this is playing the fundamental pretty loud, the second harmonic a little louder, not much of the third harmonic, not much of the fourth harmonic, a lot of the fifth harmonic. Some of that has to do with where the bow drags across the string. As the bow drags across the string, it can excite particular harmonics depending on where the antinode for that harmonic would be. Okay, so the tonal quality of different instruments, I mean, lots of instruments can play a particular E, but the tonal quality really depends on the different harmonics that that instrument tends to play. So let's take a look on the next slide. Let's pause here for a moment and take a look at a guitar. So I'm going to go grab my guitar. I'll be right back. All right, so I've got my guitar. Let's hit collect and see what kind of FFT graph it makes. There we go. Now that's a little bit of a lower note than my voice. And so let's change the graph so that it expands it out just a little bit. And you can see again, there's that spike, and then we get a repeating pattern after that. Now you can see a spike at 200 and another spike at about 400 and 600 and 800. When you pluck a string, it's not uncommon to get a lot of the first harmonic. Now you may be wondering, what are these other spikes? Well, some of that, you might be able to hear the background noise. Some of that is actually noise from the fan of the computer. Some of that is the noise from the sounding board, and some of it's noise from the other strings. When you pluck one string, it will actually cause the other strings to vibrate. A guitar also is made to resonate at different frequencies inside, and so some of that is the air inside the actual guitar vibrating at a frequency that is close to or some fraction of the frequency of the string itself. All right, so I've put my guitar away. Let's go to the next slide and just talk about how a different kind of instrument would work. So we know that stringed instruments hold a half of a wave or a full wave, or they can hold 3/2 of waves. If we have a pipe that's open on either end, that actually is a very interesting thing to think about how it works. What happens is that the sound wave itself, traveling at about 340 meters per second, oscillates back and forth, and every time it hits the opening, it reflects back, and a compression reflects as a rarefaction, and rarefaction reflects as a compression back and forth and back and forth. Now, as that wave goes back and forth, it can interfere with itself on the inside. And what you see here is that these pictures in the notes look a lot like the pictures of a string, only they're shifted by a quarter of a wavelength. Instead of having a node on the end, they have antinodes at the end because the air is free to vibrate at the ends. And they can still have a pattern of nodes where the vibrations coming from opposite directions can cancel as they pass through each other. And so you can still get standing waves, but standing waves made of sound waves themselves rather than mechanical waves in the string. Now, because this is half of a wave, crest, equilibrium, trough is only half of a wave, we still have the same relationship, wavelength is 2L. When we get to the second harmonic, crest, equilibrium, trough, equilibrium, crest, we've got the full repeating pattern of the wave. So we've got the whole length of the pipe holds one wave, that's the second harmonic. Well, these equations here match perfectly the same equations that we had for a string 2 slides back. And so the same equations predict which frequencies a tube can make. And if you think about it, this makes a lot of sense. We can vary the wavelength with the length of the pipe. Of course, a tuba has a really long pipe that's all curled together, and so it can make really long waves which correspond to low frequencies. And a flute or a piccolo is a much shorter instrument, so it will hold shorter standing waves, so it produces correspondingly higher frequencies. Now, you might notice that we've got a little, like, this is almost equal to. One of the reasons is the actual end of the pipe is not quite where the wave ends up reflects. It goes out just a little bit before it reflects in. And so the effective length of the pipe is just a little longer than the actual pipe itself. This is why if you play a brass instrument, you know that there's a little adjustment for how long you can make the pipe. That adjustment is there so that you can adjust for the different speeds of sound and also adjust for the fact that the wave doesn't really correspond to precisely the length. You can adjust that length to keep it in tune. All right, so we can use the same ideas here, that the fundamental frequency, the lowest note that a brass instrument can play, will correspond to the length of a wave that's twice as long as the instrument itself, and then all the harmonics it can play will be overtones of that are simply whole number multiples. So let me show you that in forced resonance 2. Let's press pause here. Okay, so I've got a pipe here that's open on both ends. I'm going to take this little cap off so that the sound could enter and reflect off of that side. And I'm going to drive it with a speaker. Now, if I just tap this, you don't hear it because it's not a mechanical wave. It's actually the sound inside. So I'm going to run a sound wave through this. You might be able to hear it, but this isn't one of the resonant frequencies of this pipe, so it might be pretty quiet. Now, if I run it at a frequency that matches the resonant frequency of the pipe, I'll be pulsing in energy at just the right frequency so that it resonates as a standing wave. And you can hear it's getting a lot louder at that frequency. Now, if I try and drive this pipe at a different frequency, you can see it gets quieter again. But if I go to the second harmonic, you can hear it gets loud again. So if I were able, I'll turn that down, to put a mouthpiece on this pipe, just like you would have for a flute or for a clarinet, and I was to agitate the air inside, it's those particular frequencies that would resonate. So you can imagine that some instruments take advantage of this directly. If you think about a trombone, as you play a trombone, you're literally lengthening and shortening the pipe. And all the other brass instruments that have valves, you're simply opening up and closing different pipes to adjust the length of the standing waves inside. All right, we're back. So there is one final kind of instrument that I want to show you, and it's an instrument that always sounds a little funny to our ears, and that instrument is what we call a 4L device. Now, a 4L device is asymmetrical, so where the pipe that was open at both ends, the wave reflects the same way at both sides. For a string, the string is held at both ends, and so you'll have nodes at both ends. But if you have an instrument like a music box, where the metal tine is fixed at one end, that's where there'll be a node for the standing wave. And then if you've ever looked inside a music box, there's these little metal tines that pluck these pieces of metal on the comb, and then they vibrate back and forth as a transverse wave. Well, as it turns out, those can't hold halves of waves. They hold a fourth of the wave from node to antinode at any one moment, or 3/4 of a wave, or 5/4 of a wave. So 4L devices like this, like the reed of a clarinet, it vibrates this way. It will produce only the 3rd, 5th, and 7th harmonics. Now, the body of a clarinet can be tuned to fill in the gaps, and so if you play a clarinet, you might hear the 2nd, 4th, and 6th harmonics, but the actual reed itself behaves as a 4L device, and so do a few other devices. We think of these pipes as being open on one end, so where we think about when we say an open pipe, we mean a pipe that's open on both sides. It would be hard to play a musical instrument that doesn't have any openings on either side. When we think about an instrument that's closed-ended, we think about it as closed-ended on one side. So I've got such a device. It's called a slide whistle. So let's show you this. Let's make the picture a little bit bigger so that you can see it. All right, here we go. So a slide whistle, you just blow into this side. Air is going to oscillate here, so there'll be an antinode. And then on the other side of this, you can see that there's a device that just closes it off. So this felt on the tip here seals it up. So this acts as an open-closed pipe. Open here where the air can oscillate, closed wherever the stick is on the inside. And you can see that when I play it, if I lengthen the pipe by pulling this piece out, that makes the space inside of here much longer, but it plays a lower note. So a slide whistle is a 4L device. You wouldn't expect it to make 2nd and 4th harmonics. So when we look at an FFT graph of a 4L device, guitar is a 2L device. That means it can hold a wave that is twice as long as the string itself. You see fundamental, 2nd harmonic, 3rd harmonic, 4th, and so on. For a clarinet, here's the fundamental, and then the 2nd harmonic's missing. Here's the 3rd harmonic, and the 4th harmonic is missing. Here's the 5th harmonic, and the 6th harmonic is mostly missing. So these 4L devices, they play only odd numbered multiples, and so they sound kind of hollow. They're missing some of the musicality that we would expect. The reason for that is because the waves reflect. So here's a 4L device, and you can see the waves are traveling down, they reflect, and when they come back as the opposite kind of crest or trough. So a rarefaction reflects back as a compression, then it bounces back as a compression again. So off of this end here, because it alternates whether it's a compression or a rarefaction, the wave actually has to go back and forth 4 times for the cycle to repeat. And so the wave is actually 4 times longer than the pipe itself. These can be made to make much lower notes for the same length. So if you were building one of those large pipe organs in a church that you see and you wanted a very low note, but you didn't have a lot of space, you might make the tube a closed tube so that the air inside would oscillate at a lower note and it could be shorter. All right, so how do we actually play music? Let's get to this last slide. All right, so I just want to demo these. Let me go grab my guitar and we'll talk about the stringed instruments here. I'll be right back. Hey everybody, we're back. All right, so I've got the spectrogram up so we can kind of see that. I'm going to try and move that over move that up just a little bit so I'm not on top of it. It's not on top of me. There we go. Let's go on the medium. So these thicker strings with more mass, the wave moves slower. Now the standing waves on a guitar are about the same length because the length of the strings are basically the same. So if the wave is slower like it is through a thicker material, it makes a lower note. Whereas if the string is a little thinner, we get a higher note. So on the same stringed instrument, the reason the strings are different thicknesses is because the thicker strings carry the waves more slowly along their length. And so even though they have about the same wavelength, they resonate at lower frequencies. All right, so changing the length of the string is the primary way we play a musical instrument. So if we put our finger down on the string, what that effectively does is it shortens the string. So when I put my finger down, now the wave can only resonate between where it's held here and where my finger pinches it off. And what that means is now shorter waves, it's going to take less time for the wave to go back and forth along that string. And so it's going to correspond to a higher frequency because it takes less time to go back and forth. All right, now changing the tension is what we do while we're tuning it. So now remember that changes in the medium will affect the speed. So if we change the speed of the wave by changing the tension, when it's a higher pitch, the greater tension makes the wave travel faster along the length. The wavelength doesn't change, but since the speed is, it oscillates at a higher frequency. And then finally, you can create harmonics by just touching the string right at the spot where a note should be. So right now I'm halfway between where the string is held here and where the string is held here. And so if I just lightly touch the string at that spot, you can hear it makes a very different sound than if I pluck it without my finger there. I'm not holding it down to pitch the string off. The wave can actually travel to this part of the string as well. I'm just lightly touching it. And what that does is it does not allow the first harmonic because the first harmonic would require the string to vibrate right there. Now, vocal cords work much like strings. I've put a video link to a YouTube video of people singing. It's not for the squeamish, so make sure you're ready for it. It takes an otoscope, goes up to the nose, and I recommend you take a look at that. Brows and mouthpieces, we can adjust the wavelengths in much the same way that we adjust a string. We adjust the length of the instrument. We put an opening where a hole is on a brass instrument. That's kind of like putting a finger down on a string. It effectively shortens the pipe because it forces an antinote at that spot. I really appreciate you hanging with me. This is a long lesson, lots of interesting things. I'm going to give you an opportunity, if you are musical, to share your music with the world, and I hope you do so. Looking forward to seeing some of your work. Thanks. That's another episode of Mustang Physics. We'll see you soon.